Okay. Well, thank you for this introduction and for inviting me to speak at your interesting workshop. So, so in my talk, is it in focus? Yeah. Okay. So in my talk, I wanted to talk about applications of topology or connections between topology, more specifically combinatorial topology, and distributed compute. That's just for recording. Okay, louder.
Speak louder. Speak louder. That's not an amplifier. It's just to record your voice.
Okay. So I'll talk about connections between topology, more specifically combinatorial topology, and distributed computing. Okay. So I used to have a slide explaining what we're doing in combinatorial topology, but I don't for this meeting because I figured it's an applied topology. But one of the things we do is that we look at simplicial complexes, where there is also meaning to simplices. So usually, actually, these complexes are finite, and there is some meaning for what the simplices mean, and usually it's some combinatorial meaning. So maybe this is some graphs with colorings or something of that sort. And this will be also the complexes which I will have in my talk, and their meaning will come from the theory of computation, of what the simplices mean. Now, I do think I need to talk for some time about what we mean by theoretical distributed computing. So, and there are different terms which get confused. So, for example, there's parallel computing and distributed computing. So this parallel computing is not what we are looking at. So we are not trying to take one task and break it into smaller tasks and solve it on some network or something like that. So in fact, I think the term computing itself is confusing, but that's a standard term people use. Rather, what we try to solve are coordinating tasks. Okay. So, so there will be n processes which are performing a certain task, and this task is really, from the point of view of computation, really primitive. So for example, they start with binary value 0, 1, and in the end of the performance, whatever they're doing, they need to agree on one value. Okay, so it's really much more to do with coordination rather than with actual computation. Okay, so this is by now maybe a classical subject. Maybe I should say a few words about how this came about in computer science. So this is actually just a subfield of theoretical computer science. Theoretical distributed computing is just one field. And the way it came about is that people started to construct networks at some point in the 60s and communicate over a network. Originally, actually, it was this first model of communication called message passing, where they simply have nodes and they send messages between the nodes. But if you actually want to do it somewhat realistically, the messages, they need to make assumptions about what happens. It may take a long time for messages to arrive, but they don't want bad things to happen, like if you send 2 messages in a row, then the second one arrives before the first one, so things like that. And at some point, people started to realize that some of the very basic tasks which they want to solve, so for example, the consensus task, which I'll talk about in a second, people proved that you cannot solve them using the standard model of computation. So whatever they're doing, it will not solve. There's no way to solve this task within this model. And at this point, people started to realize that they need to have more theory and to have to really have formal assumptions and to see what can you do in different systems. So what they developed is a collection of so-called standard tasks. Okay, so I'll say a few of them. There are more than that. And then when they want to test or when they want to understand something about a model of computation, then one way to understand something about it is to see which of the tasks can be solved in this model and which cannot be solved. And once you know that they can be solved, another question is how long does it take? So questions of complexity. So it's of course classical questions in any theory of computation, solvability and complexity. Okay, so like I say, the classical model is so-called message passing. Another model, the one we talk about today, or I'll talk about today, is so-called Readwrite shared memory model. So in this model, you have, let's say you have some shared memory, and then you have n processes, and what they do is, so let's say I have a shared memory, let's say it has 5 registers, so then I have 5 processes, and each process can perform one of the 2 operations. So one operation he can do is he can write his input value, so each one has an input value, and he can write it to his register. And another operation which each process can do is to read from memory. Now, in the model we'll look at is that each process can read the entire memory at once. You could, okay, you immediately see the different models. You could also say that an atomic step would be to read a specific cell, but there are theorems saying that they're computationally equivalent. So this is a model we'll look at. So.
But it can only write his portion of the memory. It can't
Right.
overwrite somebody else's.
No. Right. You could do the 2, but I think it will be just equivalent. Okay. Yeah. Okay. So that's right. So we have to fix the model, right? The model is this. Now this all happens in time. So there is a time component. So what means is that which means that you have maybe many of them, and they just start each has its own program, which we call the distributed protocol. And then he just starts doing something. He writes, for example, then he reads, then he sees what others maybe has written, then he decides something else, and so on. So he goes on in his distributed protocol, and we don't know who does what first. So for example, even if we have just 2 processes, and each one has a very simple protocol, namely, he just writes his value, and then he reads, and then maybe as a last step, he decides something about what he has seen. So just for the 2 processes, there are actually 3 possibilities of what can happen. Okay, so the possibilities we can symbolically just summarize like this. So it can happen that first the first process writes, then he reads, then the second process writes, then he reads. Then the other possibility is, obviously, if they do it in the opposite order. And the third possibility is this. Right, and there are no other options, because in principle, of course, you could also ask that, for example, to perform that here I have the first one writes and then the second one writes, but it can also happen in the opposite order, but nobody will tell the difference. And if you have an execution, so think like that, I would call an execution. This is execution thread of the protocol. This is a protocol. This is execution thread. There's 3 execution threads for this protocol if you have 2 processes. And we don't distinguish between execution threads if nobody can tell the difference. Okay, so there are 3 possible execution threads. However, we do have, for example, if you just look at the first execution thread and the last one, then the second process will not tell the difference, right? Because in each one, when he reads, okay, all he sees is that he reads the memory, and in each one he'll just see both input values. Okay, because in the first case, the first process has read the memory and he hasn't seen the input of the second one, but this he will not be able to communicate anymore because his protocol has finished. So the view of each process in this distributed computing is always an incomplete information. Okay. Now, just before I go through fixing everything, because if you want to prove something, you want to fix everything, just as a general idea, the idea to connect distributed computing and topology is to have a simplex for each execution execution thread or just execution. We have a simplex. And the vertices here correspond to process views so the number of them for each simplex will be the same as the number of processes. Okay, so if I have 3 processes, I'll have triangles. And then the way I go to simplicial complex is that I identify the views. So it may well happen, like it did here, that there will be views of a process, and he doesn't see the difference. It can correspond to different executions. So then we just glue the simplices together at this lower dimensional simplex. Okay. So unfortunately, there is no easy interpretation of simplices of dimensions between 0 and the top dimension, because these are sort of collections of partial views. But yeah, that's how it is. So for example, in this case, for this protocol, we will have a simplicial complex which will consist of 3 edges, and each edge will correspond to one of the executions, and each vertex will correspond to a view of a process. There are 4 vertices. 2 of them correspond to views of process number 1, and 2 of them correspond to views of process number 2. And the only thing which a process can see in such a very simple protocol, of course, is he just looks at the memory, he sees his value because he's just written it, and he either sees or does not the value of the other guy. Okay. So it's simply 2 possibilities, and they correspond to 2 vertices. Okay. Now, if he sees only his own value, then he knows actually which execution it is. But if he sees both values, then he doesn't.
Sorry, can you give an example? I'm confused. Can you give an example?
Of?
Like, are you saying like this W1, R1, W2, R2? How does that relate to this picture?
Right. This is this one. Okay.
Can you explain what that means on the picture?
Okay, I put labels. So names for simplices, for top dimensional simplices, in this case intervals, edges, and the names are executions. Okay, and the next step I have to tell how to glue them together along lower dimensional simplices.
What are the vertices corresponds to them?
Right, so the vertices correspond to the views of the processes.
In an example, can you relate to that?
Sure. So for example, this vertex corresponds to the process 1.
So what's the process then?
There are 2 processes. This is a protocol. This is a protocol. Write, read, and then decide. And there are 2 processes which have names 1 and 2. And this vertex corresponds to the following statement verbally. Process number 1 sees both inputs.
Because each processor is allowed to see all the inputs, and there's only 2 inputs.
He reads the memory. In this particular case, what happens is that first they each write, and then they each read. So in this execution, he will see both inputs.
Because they both read.
Because they all write.
And then he sees the result.
That's exactly right.
So now you need to tell us what the next simplex is and why it has the same vertex.
That's exactly right. So there is one other execution where the process 1 sees both values. And this is the execution where this happened. Yeah, probably there is some dead angle here.
Because in that process, number 1 sees both rights.
Right.
Comes after both.
And number 2 sees only his own,
And number 2.
which corresponds to this vertex, which says process 2 sees only himself. Right. So in particular, if he sees only himself, there is only one execution which corresponds to that, if there are 2 processes. If there are 3 processes, there are more execution than that, which correspond to the statement process 2 sees only himself, because he doesn't know what happens with 1 and 3. There's 3 options what happens to them.
Yeah, with 3 processes, you get an odd division, or you get.
Okay. So this is actually exactly a good question. So for 3 processes, you get this subdivision of a triangle. So there are 13 possibilities. With this protocol. As you see, this as a strings, and you can label them differently, and you can count how many they are. There are very many, but you can. It's a well-known number. It's called, I think, the different names. One is Fubini number. It's a number of weak orderings on n elements. So here, if I have, here's 1, 2, 2, 1, and here's 1, 2. Right. So these are weak orderings between two elements. Either one is less than 2, 2 less than 1, or they're equal. Okay, so the next one is 13, and it grows very fast. It grows faster than the exponential. It grows faster than the factorial by exponential. Okay, so if it's 6, then it's a little more. It's more than 4,000, if I remember right, for 6 processes to interact, if they only interact once. But you can prove that for this product, you always get a subdivision of a simplex, which you can also construct in an inductive way. It's always the same. You just put in a simplex in the middle, and you twist it, and then you repeat it recursively on all the lower dimensional. You can show that it's a subdivision because you can interpret it as a Schlegel diagram, which you just iterate, and so it's automatically subdivision. Otherwise, it's actually not so easy. So sometimes to show that abstractly given simplicial complex is a subdivision, linear subdivision. But here it is.
The vertices you haven't labeled, or they?
I could label them. That's right. So, so they are. So first of all, in this kind of subdivision, the vertices can be colored. Here, they can be colored by 3 colors. Whenever we say colored, we mean if 2 vertices are connected by an edge, then they get different colors, right? So other than in the bodycentric subdivision, here we can get away with 3 colors. And for example, okay, so if I now start it with 1, 2, so then I should continue. So there are 4 vertices which have color 1. And symmetrically, if you just repeat it, there will be 12 vertices in total, 3 of them. 4 of them of each color, and these 4 vertices. The colors are names of processes. So these are the 4 vertices for process number 1, and they correspond to what he sees. And it's actually obvious what can a process see, because if you only execute once, all he sees is a subset, right? He just sees inputs, including his own input. So there are 4 possibilities. In general, there are 2 to the n-1 possibilities. This vertex corresponds to the fact that the first process sees everybody else. The middle simplex corresponds to execution where everybody sees everybody. Okay? All right, so this is just a general idea. Okay, and it's of course a very general idea if you think about it, because what you can do is that you can take any model, any set of executions, as long as you can talk about partial views and so on, you can just construct a simplicial complex where simplices will correspond to possible execution threads of given protocol, and vertices correspond to local views of the processes.
So you're saying the middle one would be W1, W2, W3, R1, R2, R3?
Yes.
Because all 3 of those guys
That's right.
read what all 3 of them wrote.
That's right. That's right. But for example, one other information here is that if the first guy sees everybody, he doesn't know which of the 6 executions took place.
So each of those simplices is labeled with a combination of W's and R's.
Yes, that's exactly right. Yes. Yeah. Okay. So this is just an idea. And so this is a read-write model. And, well, OK, so then usually one has to fix a little more, because you see, if they execute only once, yeah, well, if it's only two processes, you don't see the difference yet. But if you start with three, then there are different things which can happen. You have to put conditions. You have to decide what do you allow in these executions. So do you allow just any string of reads and writes bound to the condition that there are more writes than reads at any given point by each process? Or do you have more conditions? And usually, so you can do either one. There is no right. But usually to get good topology, you need to put more conditions. Fortunately, the models you get are computationally equivalent, so you don't actually lose anything from the point of view of computation. But this is another assumption which we always make, a so-called immediate snapshot. And this just means that the executions are actually structured that not only it's the strings of W's and R's, but in fact they come in blocks. So there will be a block where a subgroup of processes writes, and then immediately the same subgroup of processes reads. Okay, it doesn't have to be this way, but that's what we assume. If you assume that, then we get nice topology. If we don't assume that, we get simplicial complex, which is, I don't even think people know what topology of that is. It's probably constructible, but okay, then the other thing you have to fix is what you allow for failures. So usually in these models, to say anything meaningful, you have to allow failures. Otherwise, if nobody fails, and you can just wait for everybody to write his stuff, and then you read it, and then you're done. So this is the whole point, right? So there is a word which is not on the slide, which is very important in this context, and this is the word wait-free. I don't know if it's two words, but this is something which has been introduced in the 80s in the distributed computing, wait-free computation. And this is a computation when you have failures, and you have, at the same time, you may have slow processes. As a process, you're participating, and you're communicating. At some point, you have to make a decision, and you don't have a complete information. It may well be that the fact that you didn't hear from somebody may well mean that he will later, he's alive, he's just very slow. So you don't know if he's very slow or if he crashed. You don't know that. And you have to make decisions under uncertainty. So I would probably prefer to call the whole thing coordination under uncertainty, but that's not what the standard term is. There are more complicated failures which people allow, called Byzantine failures, where instead of crashing, the processes are allowed to start writing bad information, and so on. So these are more complicated to take care of. And there are different timing models, and so on. So we want to fix one. So let me again say what I want to fix for this. So there are different theorems which I will not talk about, which prove equivalences between different computational models. So just the fact that we fix it doesn't mean that we are losing a lot. So once again, so the process communicates via shared memory using two operations. One was called write, and the other one is called snapshot read. We allow crash failures. And all the protocols which we look at are synchronous, wait-free. So there is no upper bound on how long it takes to wait. All executions are immediate snapshot. And then one other condition, if we want to get this picture, I can show you pictures of which you get if you don't make this assumption. But we also assume that all executions are layered, which can be phrased in two different ways. One way to phrase it is that this is for the if you have more rounds than that. This is one round. But if you have several rounds, then you can make additional assumption that each time a process does a new round, he picks a fresh. The memory comes in several strips, and then he takes the next strip and he continues with that, rather than writing into the old memory. It will give you much nicer topology, and computation it will be equivalent. So this is an assumption. Okay, so here I have an example of such a distributed task which needs to be solved. So there are different applications, of course, but here is one way to phrase it. You have a certain number of communication channels, and the number of channels is much smaller that the number of potential users, so let's say you have, well, I don't know, maybe 3 to 10, I don't know how many communication channels, but you have maybe 1 million of potential processes with process IDs which can arrive and ask for a channel to be assigned. And the question is, how many channels do we need if we have a bound on how many of them arrive at the same time? So obviously, if I have maybe 1 million potential, but let's say I know that not more than 2 or not more than 3 arrive at each time. So obviously, I cannot do fewer than 3 channels if I know that. So let's say for 2. This is a question. I know that at most 2 show up. At most 2. How many channels do I need to assign to them? OK. So one can show that that you cannot do with 2. So OK, so let me try to explain this. So let's say you have two processes, P1 and P2. Well, of course, if you want to show you cannot do it, you have to show it for any protocol. But let me try to explain why you cannot do it with this first protocol. So let's say you have 2 guys, and then each shows up, and he tells his ID, and then he looks what's going on, and he grabs a channel identity, OK, ID. So for example, he can perform, just as an example, the following protocol. He comes, he writes his ID, he looks. If he doesn't see anybody else, he just grabs the first channel, C1, and then he's done. OK. OK, what happens if he sees both? Well, let's say if he sees both, he grabs the second one, OK, C2. OK. This will not work because you have these executions, which we just discussed, in which case both of them will see each other, so they cannot just each grab the second channel then. Okay, so then you can modify it and you say, okay, well, okay, if you see both, they're allowed to compare their IDs, so you compare your ID to the other guy. If your ID is smaller, you pick the smaller channel. If your ID is bigger, you pick the bigger channel. This will work then for this execution because they'll each other and then they decide good different channels. But there are other executions where it will not work. So this particular thing will not work if you have, let's see, so if you have this execution, okay, what happens here? First the second guy comes. He doesn't see the other guy. He grabs the first channel. Then comes the second, process number 1. He comes. He sees both. He sees that his ID is smaller, and he picks the first one as well. So this is a problem. OK, and you see already from this awkward arguments which I'm giving that if you're trying to prove anything here, you will end up with very lengthy verbal arguments. First of all, depending on what they're doing, depending on the protocol, depending on all possible executions. So it is possible to write down, but it is prone to mistakes and so on. So it is much easier to phrase this kind of questions in terms of simplicial complexes and in terms of asking something about simplicial complexes. This particular question, which is kind of awkward to think about in terms of communication, is a much simpler question once you start to formulate it in terms of complexes. Because all it does is that it says, OK, if you have a protocol, let's say this particular protocol, if it's a different protocol, it will be just a little bit finer subdivision of this edge. And the only condition is that you put here labels which are channel numbers. So let's say you have C1, C2, and so on. So you put something like this. You're assigning. So each vertex here is a final state of a process. Right. So when the process ran the protocol, he needs to decide which channel he picks. So he just writes his decision on top. So all we're talking about here are labelings of vertices in the simplicial complex, in this particular simplicial complex, with the conditions. And there are 2 conditions. One condition is that if you have an edge, which means there is an execution, where process number 1 has this view and process number 2 has this view, they must get different channels. This is a condition which you know very well. It just means it's a coloring. Okay? And the second condition is that on the end vertices, it must be the same value. Because we're looking at the protocols, they're not allowed to use, they're only allowed to compare their IDs with each other. So if the both don't see each other, so this execution means P1 doesn't see the other guy. This execution means P2 doesn't see the other guy. So then, under this model, they must make the same decision because they don't know about the other guy. They know nothing. So then, here it just becomes a question, can I color this simplicial complex with two colors so that each edge has different colors and the endpoints have the same color? And the answer is no. Okay, and then the question, how many do I need? The answer is 3. Okay, if you had a protocol where, for example, they repeated this instead of doing just once, they try to fix it and just repeat a few rounds. All that will happen is that you will subdivide this further. This is what happens if you take this protocol and iterate it. You just iterate the subdivision, which we call the standard chromatic subdivision. And in the end of the day, you will be asking, you have a subdivision of an edge into an, 3 to the t edges, where t is the number of rounds. And can you color, yes or no? And the answer is still no, because it's an odd number. Okay? So you can formulate this. This is called the renaming task. Renaming task. Okay, so I think maybe it's better if I say something here rather than following the slide now. So I could ask, let me continue with this question. Okay, so this is a question for the interval. For the interval, we understand it very well. How many colors do I need? Let me ask it for a triangle. So for a triangle, it means I take triangle, I subdivide it like this. Okay, I call this a standard chromatic subdivision of the triangle. Okay, and I'm allowed to subdivide it, to iterate the subdivisions. Okay, and now I want to do the same as above. I'm asking, can I put the names, the colors, on the vertices here so that this condition is satisfied? So any triangle will have 3 different colors. The condition on the ends is also satisfied, so I have the same color on the ends. And there's one more condition, because now that I have 3 processes, they're different. For example, this edge, okay, this is process 1, this is process 2. This edge corresponds to executions where process 1 and process 2 execute. They possibly see each other, but they never see the third guy. Okay, so what happens in this sub-universe? It just means we have 2 guys, and they have IDs. This ID is smaller than this one. Now, this sub-universe is equivalent to this sub-universe, where process 1 and process 3 executed. They don't see the other guy. They cannot tell the difference if it's this or that. So therefore, if on these 2 edges, the labels should be the same in this order. So basically, if I put the labels here, then they're fixed here as well. And they're fixed here as well, in this direction. Okay. And the question is the same. Can I, the question is how many do I need? How many colors do I need to color these vertices? And you can, so here we needed 3. For a triangle, you can show that 5 is the right answer. So you can, there exists t, so, okay, the number of colors which you need, when t grows, the number of colors does not increase, which means it converges, right? Because it may decrease a little bit, but it's bound by 0 formula. Okay, so there is a limit. So the limit as t goes to infinity, in this case, of number of colors you need is 5. You can show that. And you can show that it is 2n minus 1 2n minus 1, where n is the number of vertices. and n is a prime power. Okay. And this limit, this is the question. This is a question for, this is equivalent to the distributed task. Okay, so the distributed task, the naming task is this. As a way they use, as they say it, is that you have a universe of values, you have so many processes, how many new names do you need? This is an important question in the so-called renaming task. And if it is a prime power, then it is 2n minus 1. But if it's not, then it is, you can actually, it's not 2n minus 1. You can actually color with 2n minus 2. But otherwise, it's an open question. So it's not known. So the naming task is open in distributed computing. The question is how many, and this is a very important question, of course. Here I phrase it as communication channels. There are different equivalent formulations, of course. But so if you have a certain number of processes with certain ideas and they arrive and you want to rename them, how many new labels can you get away with? So this is called the renaming task, and the answer is we don't know if n is not a prime power.
How many iterations do you need to get to 5?
No. Yeah. So this is actually a good question. So this is another question. How many iterations you need is the number of rounds you need in the communication protocol. So that's a question of, if you want, time complexity. If that, yeah. So both questions are important. What's the limit? Because it's a question of solvability. The way they phrase it is that they don't actually say what they say. Is it solvable? Is it possible for this value to do that? But that's the same question, of course. Yeah. So the first question is a question of solvability, and the second question is a question of complexity. Right. Yeah.
Any partial results for small numbers n that are not prime powers?
What's the smallest number which is not a prime power?
6.
You know how many simplices there are. So yeah. So so actually for 6, there are two possibilities, and I don't think it's known which one it is. Right. If it's what, 10 or 9, I'm not sure they know. Okay. So let me tell you maybe a related task, which is somewhat simpler than that, where we've been recently have succeeded to understand something, but it's still far from being clear. And the question is this. Okay, so maybe I'll just formulate it, because yeah, I see. The question is this. The question is, so I make the same picture. Let me first say the topological question, a simplicial question, and then I tell you what it means in distributed computing. Okay. So the question is this. So I have what I just defined. This is what we call a standard chromatic subdivision of a triangle. In general, we have standard chromatic subdivisions of any simplex, of any dimension, okay, which we can iterate. Okay. So let's say I iterate t times. And now, instead of putting colors, what I'm doing is I'm putting value 0, 1. So 0, 1 assignment on vertices subject to the following conditions. Okay. The first condition is that the top dimensional simplices are not monochromatic, which means in this particular case, if I pick any triangle, well, actually, what I would much prefer would take the second one, but it will be too cluttered if I just iterate this now here. But on this one, I can also. Okay, so if I take, say, some triangle here, then I'm not allowed to use the same label 0 and 1 on each triangle. Okay, for higher dimensions, on any simplex, I'm not allowed to use the same labels. Okay, that's the first condition. The condition is similar to this one, which for triangle means the following. the labels on the vertices of the triangle, on the end vertices, the big, must be the same. So I can as well pick 0. And then I have I can identify the edges in this direction. Okay. The direction I choose, I have underlying names. This is process 1, 2, 3. So you can say this is a smaller label, this is a bigger. So I always orient from the smaller to the bigger. Yeah. For higher dimensions, you can imagine it just means I have an ordering on a on the underlying lower dimensional simplex. Okay. And the condition is that the labels, if I have a labeling on this edge, it forces the labeling on this ones as well. So if I have 0, 1 here, then it must be 0, 1 here as well. Must be 0, 1 here. So this is actually not allowed. So it should be 0, 1. Okay. For higher dimensions.
So no matter how many subdivisions, this is just on the largest.
That's exactly right. That's why I'm saying I would prefer the second one. Right. Now for the first one is easy because there are not so many. You can just then quickly see. Yeah. Right. And for higher dimensions, it's also clear what it says. Because if I have a higher dimensional simplex, I have for any two boundary simplices of the same dimension, if I have a total ordering on the vertices, there is a unique linear isomorphism from one to the other, preserving that ordering. And the condition is that the labeling is invariant with respect to that isomorphism. Okay. So as a topologist, I prefer to think about it as not a simplicial complex, but what they call delta complex, where I have each simplex in each dimension. I have one vertex, I have one edge, I have one of each. And then then this condition just disappears. There is no condition. Then we're just talking about standard chromatic subdivisions of delta complexes. But you can also just unwind it, and this is a condition on the simplex, the equivalence. Okay, so the question. Okay, so the labeling is invariant on the boundary with respect to this, what I described. It will be too long to write this down. Okay. So the question for the edges, for example, for 2 was this, that I repeat the subdivision, and I want to put 0, 1, so that it's always different, and on the ends, it's the same. Okay. And here's the question, the answer is no, because we have an odd number of edges, no matter how many times we iterate. What about the triangle? If you, well, obviously you cannot do it once, but once you cannot do it ever, actually. But if we iterate, will it help? And so the answer is actually, for triangle as well, no. And so the answer is, yeah?
If you can't do it for the line, then you can't do it for the triangle because the line shows up as an edge of the triangle.
Right, but this condition is only for the top dimension. So you will have a monochromatic on the boundary, but then you just have to put 1 in here. Right, so for example, the way I would argue it, can I do it on this triangle? If I have here 0 and 0, it forces this one to be 1, and then I continue and I can show that it's impossible. For this t, for t equal to 1. For higher t, it's not so easy to argue. Just go through. All right? But the interesting thing is the answer. So the question is, can this be done? Okay, so let me say the question again. The question is, given n, or what this is n minus 1, given number of vertices, does there exist t so that I can do this labeling? Okay. It is a very good question, which is equivalent to it in distributed computing, because it says, given number of processes, does there exist a T-round protocol such that this task is solvable? This task is called the weak symmetry breaking task. Weak symmetry breaking task. It's called weak symmetry breaking because you're breaking the symmetry. You're starting, it's an inputless start. Each process just starts with his ID, and he just compares to those IDs. And then in the end of the day, they must be distributed into 2 groups, 0, 1, and each group must be non-empty. This is called symmetry breaking in distributed computing. Most of the time, very often, things are not possible to solve because the symmetry cannot be broken. Okay, and so actually everybody believed for a long time that this is You can never break the symmetry. But then two guys, Castaneda and Rajsbaum, showed that you can actually do it if it's not a prime power. So the answer is such a T exists if and only if the number of processes is not a prime power. This is the answer. So just to think about it, this answer consists of two parts. Okay, part number one, if number of vertices in the simplex is a prime power, then no matter how fine you subdivide, you will never be able to put labels 0 and 1 so that this is true. This is kind of an abstraction statement, and it can be proved. The proof is actually not so hard. Okay, the hard part is the other direction, which says that if the number of vertices is not a prime power, then I can actually subdivide so many times that eventually I'll put the labels. Not in the beginning, but eventually I will be able to put the labels in such a way. And
What's T for n equals 6?
What's T?
T for n equals 6.
Okay, so
Is that constructive? Or
okay, so let me give you the answer. So T for any n, yeah, is the number of rounds a protocol needs. So it's an important number. Just okay. So there was a paper, I think a few years ago, which actually got the best paper award in this principal distributed computing conferences by main people in the field, which proved upper bounds on the T, and in particular they proved that they need 7, so they can do with 17. They can do after 17 subdivisions, they can do it. Now you have to see, it will be a lot of simplices, okay? Because after the first subdivision you have, like I said, more than 4,000 for a 5 simplex. So if you do 17, it will be Z to 17. So it's a lot of simplices, okay? So last year, I proved that you can do with 3 rounds. And I also proved that you cannot do with 1. With 1 is easier, but
you
with
proved 3 for any n
no.
or for 6?
For 6.
Yeah.
Still leaves you with a lot of simplices, but and we don't. So the answer for 6 is we don't know if it's 2 or 3. I think it's probably 3, but we don't know. Okay. Now the next question you asked is also very good. Is it constructive? There's a different meaning of what is constructive and what is not for us and for them. Okay. So I can tell you my answer. I say my answer is yes, it is constructive, because if I give you a subdivision with a lot of vertices, and I describe a very complicated scheme of how to put labels, which maybe you have to go through 30 pages, then this is constructive. Non-constructive would mean I prove existence by means of some strange theorem, which we also did before with this chromatic approximation, but whenever approximation is involved, we don't, it's a non-constructive, what call non-constructive. This is not what they call constructive. What they want is a protocol, which means for each process I tell what does he do. Because you see, from their point of view, this is ridiculous, because all you have, your process, so let's say 3 rounds. All you do is that you write your value, you read, you write your value, you read, you write your value, you read. That's it. You just did that. You don't even have to do any branching, what you see in between, because you just write the entire state. You just write everything you've seen. So it's really, and so basically each process should have the roadmap. What do? I write, I read, I write, I read, I write, I read. This is what I've seen. I decide 0, 1. That's it. So the answer is there is no such protocol. We know it exists because I can construct the labeling, but there is no protocol in verbal terms, which would mean if I was the second largest in the second round, then da 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 da. That does not exist. Okay, but the thing is that right. So the T. Okay, so now, so let me. So this is a good question because I have another 10 minutes. Okay, so.
Sorry, just to clarify on the successive iteration, you don't have to impose a boundary condition on the.
Yes. Well, not inside. On the boundary.
On the
Right.
entire boundary.
Right. Just on the entire boundary. Yeah. So exactly. So they think of it as iterations, but I think of it as just a subdivision of the whole simplex. So the condition is on the boundary of the initial simplex. Okay. All right. So the question is, what is T? And we know that for n equal to 6, it is 2 or 3. Okay. And so for non-prime powers, of course, for prime powers. Okay. And they proved something, the upper bound, something like this, where Q is the largest prime power which divides n. So it's a quite large number, it's a double exponential. Now you have to, so in all of these things, usually it's like this. So the complexity is some function of n. That's how it is usually in computing. You have a number of processes, how long will it take? Some function, exponential, sub-exponential, polynomial, and so on. But here's a strange thing. So I proved that if you take n equal not just to 6, but to any multiple of 6, then you can still do with 3 rounds. Now this is something which must be false, okay? Just by any meaningful criteria, because what it says is that I have a sequence of numbers of processes which goes to infinity, but the time it takes for the protocols to solve it does not go to infinity. And what I think it's worse is that it's not true that it's in general a constant. So rather I think, and this is actually, I suggested this after we proved this, that one needs to change the whole paradigm of trying to estimate this complexity. And instead of trying to estimate the complexity in terms of n itself, I think it should be estimated in terms of solutions to a certain Diophantine equation, which is associated to n. Namely, this equation. This is an equation with binomial coefficients. It's a little bit long story to explain, but this is, so you see, it is binomial coefficients of n. You can think about it like this. You express 1 as a linear combination of binomial coefficients of n. For 6 you can do it, because you can write 1 as 6 plus 15 minus 20, which is 6 choose 1, 6 choose 2, and 6 choose 3.
Use the greatest common divisor of binomial coefficients, leaving aside 1 at the beginning. I think that the greatest common divisor, depends on whether n is prime power.
That's exactly right. That's exactly so.
Okay.
That's right. So yeah. So this is how you prove it's not possible. You reduce by means of some. That's exactly right. So you reduce by means of some argument to the fact that if the weak symmetry breaking can be solved, if I can put these values, this label 0 and 1, then these binomial coefficients will have a solution. Okay. Now, obviously, from what you said, it will not have a solution if it's a prime power, because they have a greatest common divisor not in 1, if and only if it's a prime power. So this is the end of the proof, but this is how the proof goes roughly. Now, for a long time, people have thought that this is just a feature of the argument. Okay, they're trying to prove something is impossible to compute. They reduce it, and there are situations like this. They reduce it to some mathematical statement, and the statement, unfortunately, is true only for prime powers. Okay, so they proved it for prime powers. For other things, it's true as well. They just don't know how to prove it yet. But what turned out to be here, somewhat counterintuitively, that it's actually not the case. So if it does have a solution, this Diophantine equation, then you can put this label 0 and 1. After a large number of rounds. Nobody knows how many. And what it means also, it means that there exist such protocols. It means 6 processes can break the symmetry. They have protocols. If they execute it, they will break the symmetry. But we don't know what they should do. We just know it exists. We can put the labels. I can write down what they should do, but there will be a step saying, now consult this table with 500 values. But yeah, this is my protocol. I don't know how explicit that is, but yeah. But that's exactly right. Right. So if there exists a solution, now the question is, if solution exists, how big are the coefficients? And my claim is, or my suggestion of the complexity estimate paradigm here, is that these coefficients have much more to do with the complexity than the actual n. And I see this strange theorem, which I think is true, as a confirmation of that. So for
You mean like you can estimate t in terms of the sizes of the x's?
right, minimal, yeah. That's right. So see, this is the only thing which is interesting about the 6k is that it will have a very special solution to this equation. Namely, it will 1 minus 1 0, 1 minus 1 0 periodically repeated will give a solution. So the coefficients are very small. I cannot prove. I conjecture that if it has a solution with coefficients absolute value at most 1, then you can always do it in 3 rounds. I cannot prove it in this generality. For 6t, I can't prove it. So this is, and like I said, this is a very central, this is a completely mathematical reformulation, so you can just forget about it. But if you don't want to forget about it, in distributed computing, it's a very central question. Weak symmetry breaking is a very important standard task. Symmetry breaking in general is a big topic. So, and it's one of the very few examples where the answer is counterintuitive. Most of the time, you kind of know the answer once you ask the question. You just maybe don't know yet how to prove it. But here you don't. Okay, so in fact, maybe one can, I don't even know if you can characterize all the n's for which it has a plus minus 1 0 solution, this equation. That's kind of strange. It's not something which people in number theory look that much at. But yeah. Okay, so probably I know the answer. There's a conjecture. It's what the bound is on t. But anyway, but this is the current state. So if you have 12, 18, and so on processes, you can do it with 3 rounds. So there is and the proof is kind of constructive, but it's quite complicated because you have what you do is you take a second subdivision of a 6k minus 1 simplex, second chromatic subdivision, and then you do some graph theory on it, which is quite painful actually. Some matchings and some labels and so on. So anyway, I think I should probably stop at this point.